Have you ever stopped to consider the potential hidden within an ordinary rock? We often overlook these silent giants beneath our feet, but they hold secrets that can reshape our world. Some rocks can, thanks to uranium, a naturally occurring element with extraordinary properties. It's a key ingredient in nuclear power. Uranium is a heavy metal found in the Earth's crust, distributed unevenly across the globe, waiting to be discovered. Uranium is naturally radioactive and packed with an immense amount of energy, a force waiting to be unleashed. This radioactivity is what makes it so powerful. Over decades, scientists have learned to unlock this energy safely and efficiently, pushing the boundaries of what's possible. By carefully controlling nuclear reactions, we are transforming uranium into one of the world's most powerful and reliable energy sources. Our journey follows uranium from deep underground, where it's carefully extracted, to the heart of a nuclear power plant where its energy is harnessed to generate electricity. The energy comes from the nucleus, the atom's core, the very center of matter. It is within this nucleus where uranium's large, unstable structure allows it to be split in a process called nuclear fission, releasing tremendous energy. When uranium splits or undergoes fission, it releases a burst of heat energy, which is then used to create steam and drive turbines. This entire process starts with finding uranium ore, the raw material that fuels nuclear power. Uranium ore is scattered in tiny amounts within rocks, making its discovery a challenging but rewarding endeavor. Prospectors use specialized tools like Geiger counters, sensitive instruments that can detect radiation, to detect uranium's faint radiation and pinpoint the location of rich deposits hidden beneath the surface. Once found, these deposits are carefully mined, using advanced techniques to extract the valuable ore. This marks the crucial first step in transforming a seemingly simple rock into a source of clean, reliable energy for our communities. Get ready to witness the incredible journey of uranium and see how this hidden power lights up our world, powering homes and industries. From the complexities of geology, where uranium deposits are formed over millions of years, to the intricacies of nuclear physics, which govern the behavior of atoms, uranium's journey is a compelling story of scientific discovery and technological innovation, constantly evolving to meet our energy needs. Let's dig in and discover the fascinating process of how a rock, seemingly ordinary, becomes the electricity that powers our modern lives. The story of uranium begins billions of years ago, forged in the heart of dying stars. But our journey starts much closer to home, deep underground, where this element lies hidden, waiting to be discovered. Here, dedicated geologists embark on a crucial hunt, searching for rich uranium deposits. They employ sophisticated high-tech tools like scintillometers, which are designed to detect the faint but telltale gamma rays emitted by uranium. These rays act like a beacon, guiding them to potential ore bodies. Once a promising site is identified, the next step involves careful investigation. Core samples are meticulously drilled and extracted, providing a physical record of the underground geology. These samples are then sent to labs where they are analyzed in detail to precisely map out the extent and concentration of the uranium deposit. This analysis informs critical decisions about whether and how to proceed with mining. Mining methods vary. The choice of mining technique depends largely on the depth and characteristics of the uranium deposit. Open-pit mining is typically employed for shallow deposits, while underground mining is necessary to reach deeper ones, requiring extensive tunneling and specialized equipment. There's also in-situ recovery, ISR, a gentler, more eco-friendly approach that minimizes surface disruption. ISR involves drilling wells and injecting a special solution into the uranium ore body. This solution dissolves the uranium underground, allowing it to be pumped to the surface for processing. Regardless of the mining method used, the initial product is uranium ore, rock that contains relatively small amounts of uranium compounds. This ore is then transported to a mill, a specialized processing facility, where it undergoes a series of transformations, starting with being crushed into a fine powder. This pulverization process dramatically increases the surface area of the ore, which in turn makes it significantly easier to separate the valuable uranium from the other minerals and rock. This crushed ore is the essential first step in a complex process, refining raw material into what will eventually become nuclear fuel. Throughout each stage of the mining process, there's a strong emphasis on minimizing environmental impact and employing sustainable practices, ensuring the responsible extraction of this valuable resource. And so, from deep within the earth, uranium ore emerges, ready for its next crucial transformation. the adventure is far from over. It continues as we prepare to transform this seemingly ordinary powder into something far more powerful and energy-rich. The entire process is a fascinating blend of geology, cutting-edge engineering, and a deep commitment to environmental care. Our next stop takes us into the realm of chemistry, where we'll unlock uranium's true potential and harness its incredible energy. At the mill, uranium ore is mixed with acid in a process called leaching, dissolving uranium into a liquid. The uranium-rich solution is purified using filters and ion exchange, concentrating the uranium. Next, a chemical is added to make uranium precipitate out as a solid powder. This powder, called yellow cake, is mostly uranium oxide, U3O8. Yellow cake is stable, easy to transport, and marks a huge leap from raw ore to concentrated fuel. The color can range from yellow to dark greenish black, depending on impurities. Packed into sealed drums, yellow cake is shipped to enrichment facilities. We've turned rock with less than 1% uranium into powder that's over 75% uranium. This is a major milestone in the nuclear fuel cycle. The next step, unlocking yellow cake's true power. From ore to yellow cake, uranium's transformation is well underway. Now it's time for enrichment, the key to making nuclear fuel. Yellow cake, while a significant step in the nuclear fuel cycle, isn't quite ready to power our reactors. It's like having the raw ingredients for a cake. You need to process them further before you can bake. It requires a crucial transformation. It needs enrichment. This is where the magic and the immense technical challenge truly begins. Uranium, in its natural state, is a mixture of different types of atoms, known as isotopes. The vast majority of these are U-238, making up over 99% of the total. It's the workhorse of uranium, but not the star player in nuclear fission. Then there's the rare U-235, accounting for only about 0.7%. This small fraction holds the key to unlocking nuclear energy. U-235 is special because of its unique nuclear properties. It's capable of sustaining a nuclear chain reaction, the process that releases tremendous amounts of energy. However, its scarcity in natural uranium poses a significant hurdle. To make nuclear reactors operate efficiently, most require uranium that has been enriched. This means increasing the concentration of U-235 to around 35%. This higher concentration allows for a more stable and efficient chain reaction, leading to greater energy production. Enrichment is the process that selectively increases the concentration of the U-235 isotope, effectively making the uranium reactor ready and capable of sustaining a controlled nuclear reaction. But here's the challenge. U-235 and U-238 are chemically identical, behaving in the exact same way in chemical reactions. Furthermore, they have nearly the same mass, making physical separation incredibly difficult. It's only a tiny weight difference that allows for any kind of separation at all. Think of enrichment as being similar to concentrating orange juice. You're essentially removing the water, in this case the U-238, to boost the flavor, which is the concentration of U-235. The entire process is highly technical and requires extreme precision. It relies entirely on exploiting that incredibly slight mass difference between the two isotopes. Sophisticated methods, such as using gas centrifuges, are employed. These centrifuges exploit this minute difference in mass to gradually separate the isotopes over many stages. Enrichment is a delicate and precise operation, demanding careful monitoring and control. It's the process of transforming ordinary, naturally occurring uranium into a powerful and concentrated fuel source. It's truly a marvel of modern engineering and applied physics, pushing the boundaries of what's possible. And with enriched uranium in hand, we're one significant step closer to harnessing the power of nuclear energy for clean and sustainable electricity generation. So next, let's dive deeper and see exactly how this enrichment process actually works, step by step. The isotope race, the separation of U-235 and U-238, is about to begin. Before enrichment, yellow cake is converted into a gas, uranium hexafluoride, UF6. UF6 is fed into gas centrifuges, spinning at incredible speeds. Heavier U-238 atoms move outward. Lighter U-235 atoms stay closer to the center. Thousands of centrifuges are linked in a cascade, gradually increasing U-235 concentration. After many cycles, we get two streams: enriched UF6, 35% U-235, and depleted UF6, mostly U-238. The enriched gas is ready to become nuclear fuel. Depleted uranium has other uses, but its role in the fuel cycle is done. This high-tech race separates the power-packed atoms from the rest. Now it's time to turn enriched gas into solid fuel. The transformation continues. Enriched UF6 gas is converted into a solid black powder, uranium dioxide, UO2. This powder is pressed into tiny, dense pellets, each the size of a fingertip, but packed with energy. The pellets are baked at high temperatures to become hard ceramic-like fuel. Finished pellets are ground to precise size and loaded into long metal tubes called fuel rods. Hundreds of rods are bundled into fuel assemblies. These assemblies are the building blocks of nuclear reactors. Fuel rods keep radioactive material contained while allowing heat to escape. The result? A compact, powerful fuel ready for the reactor core. Next, let's see how these pellets unleash atomic energy. Fuel assemblies are loaded into the reactor core, submerged in water for cooling and moderation. Control rods manage the chain reaction by absorbing or releasing neutrons. When a neutron hits a U-235 atom, it splits, releasing heat and more neutrons. This triggers a self-sustaining chain reaction, generating massive heat. The heat turns water into high-pressure steam. Steam spins a turbine, which drives a generator to produce electricity. Nuclear fission replaces burning fossil fuels, creating clean, reliable power. That's how uranium's hidden energy lights up our world. After years in the reactor, fuel becomes spent, less efficient, and highly radioactive. Spent fuel is removed by remote machines and stored underwater in deep pools for cooling and radiation shielding. Once cooled, it's transferred to massive dry casks, steel and concrete containers for long-term storage. Some countries recycle used fuel, extracting uranium and plutonium for new fuel. The remaining waste is vitrified, turned into stable glass, and stored deep underground. Safe management and recycling reduce waste and maximize uranium's value. The fuel cycle continues with science ensuring safety at every step. From rock to reactor, uranium's journey is a triumph of science and engineering. Nuclear power delivers huge amounts of clean energy with minimal waste. Just one fuel assembly can power a city for years, without greenhouse gases. New technologies like small modular reactors promise even safer, more flexible nuclear power. Recycling and advanced fuel cycles could make uranium even more sustainable. Uranium's story is still unfolding, lighting the way to a cleaner future. Next time you flip a switch, remember the incredible science behind that energy. Sometimes the smallest atoms hold the brightest promise for our world.